on set theory, just going to start with the definition. What are sets? So a set is any well-defined collection of objects. Any well-defined collection of objects. Any list of objects or a collection of objects, we can call it what? A set. Can call it what? A set. I just need a highlighter, not a pen. Okay, so for it to be a set, it must be a collection of what? Of objects. This keyword, it must be a collection of objects so that it can be what? A set. Tim, can we make sure that let's make sure that we are all on mute. Thank you. Okay, so the elements of a set are the objects in a set. There's this keyword that we actually keep on repeating using, which are the elements of a set. What are the elements of a set? So those are objects, that can make a set, those are the elements of what? Of a set. So the elements of a set are the objects in a set. So there are some notations that we use when you are describing sets. There are some notations that we usually use when you are describing a set. So usually we denote sets with uppercase letters, elements with lowercase letters. So whenever you have a set, the set name, we normally use the uppercase letter. We do not set using an uppercase letter. And then for the elements, we normally use the lowercase letters. So the following notation is used to show set membership. Whenever you want to show that this element belongs to this set, X belongs to set A or X belongs to set B, we normally use this notation. We use this notation with this symbol here, this symbol that we have here, which says X is an element of A, or X is a member of what? Of A. Here, it means that the X that we have is a member of what? Of A. And we also use this symbol which says X is not the member, or X is not an element of A, which means that X is not an element of A. What we're actually saying is that for all the objects that we have which are in A, X is not one of them, in simple terms. So what are the ways we have of describing sets? There are people who are trying to join now. I think if we add them, we actually end up having those problems. They will be not obeying the ground rules that we actually set earlier. So what are the ways of describing sets, or ways that we can use to describe sets? So ways of describing sets, there's what we call the roster method. The roster method, and I'm sure that is the easiest way, and is the way that we are all mostly used with. So there's what we call the roster method. This one. This one lists the elements inside the curly brackets. Here you have got this A, which will be representing the set, so that you can identify the set as what? As A. And then you've got this list of elements inside curly brackets, inside the curly brackets, and they are comma separated. You use a comma to separate them. Don't need to see a semicolon there. So there's what we call as well the set builder notation. The set builder notation. This one now, there will be some words which will be describing the characteristics of the objects of that set. So this one characterizes all those elements in the set by stating the property or properties they must have to be members. So with this one, what you just do is to define those objects using their properties. What are they going to have so that they can fall under this set? So, for example, here we've got this set A, which says that X is such that X is an odd positive integer less than 10. What does it mean is that this set A is going to take all the elements, all the odd numbers, sorry, all the odd positive integers which are less than 10, which means you'll be starting from 0, or 0 is also a positive odd integer. So you start from 0 up to 9, because it says less than 10. Also, there is the descriptive form. This one is the verbal. So give a verbal description, for example. So this one will be given a statement. There will be these curly braces or so. What will be just given is what? It's just a description. So X, set X is equal to A is the set of all integers from 1 to 6 inclusive. Inclusive, which means we'll be considering all the integers from 1 to 6, including the boundaries, which are 1 and 6, which means we'll be starting from 1 as well as up to 6, as well as 6 included. So those are the ways of describing sets, and those are the ways that we'll be actually using in this module. I don't know if there are any questions there. So let's talk about the common sets numbers, common sets of numbers, common sets of numbers. So there are common sets that we expect you to know. So there is this one, which is represented by N, which is the set of natural numbers, and then you've got the set here, which is the set of integers, and we've got a Q, which is the set of what? Of rational numbers. So you need to know the boundaries of these sets, of these sets. Like if you are saying natural numbers, what are these natural numbers? What are the set of integers? What is contained in the set of what? Of integers. Also, we've got the set of rational numbers, the set of real numbers, as well as the complex numbers. Though we do not dwell much on this set of complex numbers in this module. So from there, we have got some special sets that you have to know. There are some special sets that you have to know. Special sets that you have to know. What are these special sets? So there's what we call the null set or an empty set. The null set or the empty set. So this is a set with no elements. It's just a set without elements, and it is often symbolized by that phi. This one, this symbol. 0 akachekwa nditi, or just empty curly braces. If you just write this curly braces without any element within it, you'll be actually representing it will be actually representing an empty set. An empty set. So there's what we call a universal set. There's what we call a universal set. So the universal set, this is the set of all elements currently under consideration. Under consideration, and is often symbolized by this U or this symbol, which is like an epsilon, but it's not an epsilon. So we use those symbols to represent the universal set. So your universal set, it will be the set of all elements which are currently under consideration. So let's talk about the membership relationships. Membership relationships. There's what we call membership relationships. Yeah. So let's talk about the subset. A subset. the definition of a subset. If we say A is a subset of B, or A is a proper subset of B, what we'll be actually talking about. So for a subset, we use this symbol, the symbol that we have here. Says A is a subset of B. Take note of that, of this dash that we have here. It must be there for a subset. So we say A is a subset of B if X is an element of A, which implies that X is also an element of B. So that is all the elements of A are also members of B. So the notation for subset is very similar to the notation for less than or equal to, and means in terms of the sets are included in or equal to. So for A to be a subset of B, elements, all the elements in A must be also in what? In B. So all the members of A are also members of B. That's the subset. Let's talk about a proper subset. What would be actually different from the subset? So a proper subset like A is a proper subset of B. We say that A is a proper subset of B if all the members of A are also members of B, but in addition, there exists at least one element C, such that C is an element of B, but C is not an element of A. What we are saying here is just like here, you can have 1, 2, 3 as elements of B, right? As elements of B. And then we can have our A here with 1 and 2. And then we can say that A is a proper subset of B. Why? Because we've got 1 and 2, which also appear in what? In B here, but here those are all the elements that belongs to A. And after that, we also have this element which you call C, which is in B, but which is not in what? In A. So in other words, only a proper subset, the set A will be not actually equal to what? To B, or by any chance will not be equal to what? To B. That's a proper subset. Don't know if there is any question there. Can we make sure that we turn off our camera, please? Make sure that you turn off your camera. Who is that? Nyasha. Chimtapi. Make sure that you turn off your camera. Then Thomas Nyamtena, is that a hand? If so, unmute yourself.
Hello?
Yes.
So, thank you very much, sir. I would like to understand better. So in this case, are we saying that all the the difference between the proper subset and the subset is on the contents of the elements A and B? In the first scenario, I don't know whether I got it right. You were saying if it is a subset, it means all the elements in A are also elements of set B.
Yes.
All of them.
All of them in A are part of B, but here we've got an exception that in A will be also equal to what? To B. Like here you can have 1, 2, 3 in A, and then in B we have 1, 2, 3. We actually not have an extra element in B which will be not in what? In A. That's
So
what.
in this case, they are equal sets.
Yes, we say that they are less than or equal to. It's not always the case. It's not always the case
Okay.
that A would be equal to B, so that we can say A is a proper subset of B. If we say so, it will mean that A will be equal to B, so those sets will be actually equal. But it's not always the case. But we are saying that we have got an opportunity that A will be equal to what? Will be equal to B, or will be less than B, which means A you can in A you can have elements less than elements which are in B, or we can have elements which are also in A and in B, just like that, as an equal what? Subset. But
Thank
here
you.
for a proper subset, you just have what? An extra element which will be always in B, which is not in A.
Thank you, sir.
Okay. So let's talk about the finite states and the finite sets and infinite sets. So a set S is said to be finite if it contains exactly m distinct elements where m denotes some non-negative integer. If we can manage to find the number of elements in a certain set, we can say that set is what? Is a finite set, because we can actually find its cardinality, or the number of sets, the number of elements in that set. So here in such case, we write this modulus of S is equal to M, or number of elements in S is equal to M. Whichever way you use, you'll be referring to the same thing, which is the number of elements, or the total number of elements in that set. And we call it as well the cardinality of set. So if you ask you about the cardinality of a set, we are just asking for the total elements, or the total number of elements in that set. So a set is said to be infinite if it is not finite. So in other words, if it is an endless set, you can call it what? Infinite. For example, the set S of letters of English alphabet is finite. Why? Because we have got we only have 26 alphabets. So here we can actually find the total number in that set S. But what about the set of positive integers? You can count on and count on and count on. So that set is what? Is infinite. The set of what? Of positive integers. It stretches up to positive infinity. So that's the difference between finite sets and infinite sets. Okay, so let's talk about the equal sets. Let's talk about the equal sets. So two sets are equal if and only if they have the same elements. If and only if they have the same elements. They must have the same elements for them to be equal. Not total number of elements, but same elements, like element X be equal to element X, element Y be equal to element Y. All those elements, if they are equal in set A and those in set B, then you can say that these sets are equal. So therefore, if A and B are sets, then A and B are equal. If and only if for all of X, this one is for all. For all of X, X is an element of A, which implies that X is also an element of B. So it goes both ways. If X is an element of A, also X must be an element of B. If X is an element of B, also X must be an element of what? Of A. So we write that A is equal to B if A and B are equal sets. So for example, here the sets 1, 2, 5 and the set with elements 2, 5, 1 are equal because they have the same elements. the arrangement or the order of elements in that set doesn't matter. So not the order in which the elements of a set are listed does not matter. Also, it does not matter if an element of a set is listed more than once. So this set with 1, 222, and quad 5 is the same as this set because we just have the same elements. So it's the same as the set 1, 2, 5 because they have the same elements. So let's talk about the Venn diagrams. The Venn diagrams. So sets can be represented graphically using Venn diagrams, named after the English mathematician John Venn, who introduced their use in 1881. So in Venn diagrams, the universal set U, this one, which will be the set which will contain all the elements under consideration, it is represented by a rectangle. It will be represented by a rectangle. This rectangle that we have here, just that's the rectangle, this one will be representing this U, the universal set. So anything that comes inside here, it will be a subset of what? Of the universal set.
Hello,
It will,
sir.
hello.
Oh, sorry to interrupt. I think someone is raising a hand.
And it's Xiaomar.
It is him, is Yomara.
Is that your real name?
Yes, it's a real name, sir. Sorry to take you back just a bit of the previous slide that you have just done.
Okay.
Patiri kuti apo ma-elements a1 to 5 are equal to the elements 1 triple 2 quad 5 andinonyatsobata mbichana. What if question ikauya ichibvunza kuti totiti sekuti how many elements are in set B, ngatiti set B ndorina 1 triple 2 quad 5 and then set A ndorina 1 2 5 here.
Now we are not relating to the issue of equal sets, but now we are relating to elements, like number of elements. Because here we are just talking about the issue of equal sets, not equality in terms of number of elements. This set have got what number of elements, and this set have got what number of elements. If we can count them, they are just repeating. They are just repeating, but they are 3.
So number of elements can differ from the equality of the sets.
Yes, here we are just saying if you are saying sets are equal, here if you are saying sets are equal, what will be actually under consideration is the element itself in the set. Are the elements here equal to these elements here? Like here you've got 1 2 5, and here you've got 1 2 5. Do we have any other number or any other element which is not 1 2 5 in this set? No, which means they are what? They are equal.
All right. I now understand. Thank you, sir.
You're welcome. So inside this rectangle, they are what? They are circles. They are circle or other geometrical figures which are used to represent what? Sets. So inside this rectangle, you'll be having circles as well as some elements in this rectangle. So sometimes points are used to represent the particular elements of the set, like what we are doing here. We've got this U, this A, this E, and that O and I and a V. So Venn diagrams are often used to indicate the relationships between sets. You can use this Venn diagram to actually represent the relationships between these sets. So there's what we call as a power set. A power set. You need to understand this thing very well, otherwise it will confuse you later. So given a set S, the power set of S is the set of all subsets of the set S. That's what we call a power set. So it will be a collection of all subsets of the set S. That's a power set of what? Of S. So if you are given a set S and you are being asked to find the power set of that set, you just have to list down all the subsets of that set. And mind you that the set itself is a subset of itself. Also, the empty set is also the subset of any set. So you need to include those two sets on the list of what? Of subset. So the power set of S is denoted by P of S, just like this. So for example, what is the power set of the set 0, 1, 2? The set with these elements 0, 1, 2. What could be its power set? So the power set of P, the power set P of 0, 1, 2, or a set containing these elements 0, 1, 2, is the set of all subset of this set with 0, 1, 2. Hence, this power set, you have the empty set first as the what? As the subset. Remember, in empty set, you can use this phi or empty curly braces. And remember that the elements of a power set, they are also what? Sets. So the notation here will be actually not writing 0, 1, 0, 0 outside this curly brace. So you need to put this curly brace as well. So there is a 0 as a subset of this set. There is a 1, a set with just a what? A 1 is part of this subset, is a subset of this set. And then you have a 2. Then you can take a 0, 1 and a 0, 2. You can take as well a 1, 2. And then the set itself is also a subset of that set. So this should become our subset with how many sets? 1, 2, 3, 4, 5, 6, 7, 8. It will contain 8 sets, which will give us a certain formula to find the total number of subset of a certain set. So don't confuse it with some formulas that you actually find to find a power set. That formula will only give you the total number of sets that you can generate from a certain set. So in other words, it will not give you the subset, the power set, but it will only help you to know the total number of subsets that you need to produce from that set, which will be 2 to the power n, 2 to the power total number of what? Of elements in the set that you are considering. Like here it's 2 to the power 3, which will give you what? 8. So you need to come up with what? With 8 subsets. Let's track that down. So note that the empty set and the set itself are also members of a power set. Let's take note of that. So let's talk about the Cartesian products. Cartesian products of our sets. If you have some sets, and then there's what we call a Cartesian product. So let A and B be sets, which means we've got a set A and a set B. So the Cartesian product of A and B denoted by A cross B we use this multiplication and we call it a cross B, not A times B or A blah blah blah. It's A cross B. So it's the set of all ordered pairs A, B, where A is an element of A and B is an element of B. So this Cartesian product of a set, the result will be having the elements in A being paired to the elements in B. Here we've got an A, B, where A is an element of A and B is an element of B. Hence, A cross B, or the Cartesian product of A and B, will be AB such that A is an element of A and B is an element of B. In other words, you must have, whenever you have these pairs, you need to make sure that this pair belongs to A and this pair belongs to B. Then we can have a what? A Cartesian product. So what is the Cartesian product of A with elements 1, 2 and B with elements A, B, C? As an example, we've got these two sets. You have got an 1, 2 and you have got A, B, C. So we need to come up with a what? With a Cartesian product. So the Cartesian product of A cross B is that what you do here is not actually like we are multiplying or we are expanding brackets. You see it later that it's not like that. So what you'll be doing here, you'll be taking this element and match it with all the elements here, and this element match it with all the elements here. So what you do here for the Cartesian product, at first you have got 1A, this matching this and this. Since A is our first set and B is our second set, we need to make sure that the first element will belong to A and the second element will belong to B. So here we've got 1A followed by 1B and then followed by 1C. And then later on, we've got a 2 by A and a 2 by B and a 2 by C. And that will form our Cartesian product of A and B. And take note of the notation that we use. We use these braces now, which are not the curly ones. So note that the Cartesian products of A cross B and B cross A are not equal. If we take B cross A here as B cross, as B, so B cross A, I'm just using, I'm not using a mouse. So if we have B cross A here is not equal to what? To A cross B, in the sense that we'll be actually starting with these elements, like we will have A1, A2, B1, B2, C1, C2, something like that. So it will be actually totally different from A cross B. So it will be actually only equal if and only if A is an empty set or B is an empty set, so that A cross B is a what? Is an empty set, or A is equal to B. So we only have two conditions. If one of the sets is an empty set, or when A is equal to B, when you have equal sets, the Cartesian product of A and B or B and A will be what? Will be equal. Don't know if there is any question there. So can move on to this Cartesian product. This is the formula that we have. Here we need a formula. Why? Because it is actually extending up to what? Up to n. Here we only consider two sets, but we can have as many sets as we can have. So we can have the Cartesian product of sets of A, A1, A2 up to AN, and this is the formula. that you'll be using. It's just a formula that that is there. Don't need to actually deduce the formula, but what you need to do is to be able to use this formula. So for this one, I'm just going to do an example, and then we follow that. Here, what is the Cartesian product of A cross B cross C? What is the Cartesian product of A, B, and C? Where A have got 0, 1, B have got 1, 2, C have got 0, 1, 2. So on this one, what you do, you need first to pair 0 with this element and with the rest of these elements. Then next is 0 again with this element and then with the rest of these elements. And then you go on to 1, you pair 1 with this element and the rest of these elements. 1 again with this element and the rest of this element. So how you do it here? So at the end of the day, if you have 3 sets, you need to have A, B, C, where A belongs to A, B belongs to B, and C belongs to C on each and every like a subset that you come up with. So for example, here at first we've got 0, 1, 0. Where do we get this 0, 1, 0? It's this 0. Let me see if I can have, let me use this right. We have this 0 and this 1 and this 0, like this. So it's 0, 1, 0. And then next we need this 0 and this 1 and this 1. And that's 0, 1, 1. And then next, what you need there, this 0 again, and this 1, and then this 2. That's 0, 1, 2. So what you do, you take this first element and you pair it with 1 and with the rest of this element. So it will be 0, 1, 0, 0, 1, 1, 0, 1, 2. And after that, you move on to the next element on your second set. So you pair 0 with what? With the 2, 0 with this 2. And then you pair that 0 with the 2 and with the rest of these elements. So you have 0, 2, 0 here. Or do you have 0, 2, 0? And after that, you have 0, 2, 1. To 0, and then to 1, and then to 2. 0, 2, 1, 0, 2, 2. And after that, you move on to the next element in A. We repeat the loop. You start with 1, 1, and 0, and then you pair this one with this one, with 1, and then this one, 1, and 2, which will give us 1, 1, 0, 1, 1, and 1, 1, 2. And after that, you pair this one with this element 2 here with the rest of these elements, which will be 1, 2, 0, 1, 2, 0, this 0 here, and then 1, 2, 1, and then 1, 2, 2. This is what we have here. And then you close your curly braces. So this is how do you find the what? So do you find the Cartesian product of given sets? So note that when A, B, and C are sets, A cross B cross C is not the same as A cross B cross C. Since here you need to first do the cross product and then you do the cross product again of A and B with C. I don't know if there is question here. Is it a hand? It's just Emmanuel Mzorela. Is that a hand now, or it was just a hand that you didn't bring down?
No.
Okay,
Let's
it's okay.
continue, sir.
Okay, so let's talk about the set operations. The set operations. So two or more sets can be combined in many different ways. For instance, starting with the set of mathematics majors at your school and the set of computer science majors at your school, we can form the set of students who are mathematics majors or computer science majors. So we are just saying that whenever you have got some sets, we can actually combine them. So we use set operations to combine them. So the set of students who are joint majors in mathematics and computer science can also have or form the set of all students not majoring in mathematics. So we can combine all those sets to form another set. So you've got what we call set union as a what? As a set operation, right? You've got what we call a set union. If we say A union B is the set of all elements that are in A or B or both, that's the union. I just considering all the elements which are in A and which are in B, that's the set union. So an element X belongs to the union of the sets A and B if and only if X belongs to A or X belongs to B. So the condition is that X has to be also belong to A and also can have X which will be belong to B. If we put all those elements together, we can form a what? A set union between A and B. So A union B is just is this in the form of build a set builder notation. X is such that X is an element of A or X is an element of B. Apa tungotora A na B tongobatanidza handiti? Tungobatanidza. And take note of repeating elements. If elements are repeating, when you are listing A union B, you don't need to repeat that element. You write that element once. So for the elements on the intersection, you write them once. On a Venn diagram, it will be like this. If you say shade the region, A union B, you need to shade the set A and B, including their intersection, including this part. So this is similar to the logical or operator. There's an example here of a union. The union of the sets 1, 3, 5, 1, 2, 3 is the set 1, 2, 3, 5 here. This is the union of this set and this. And take note that this 3 is repeating, but we only write it once here. So that is 1, 3, 5 union this set with 1, 2, 3. You have 1, 2, 3, 5. So the union of the set of all computer science majors at your school and the set of all mathematics majors at your school is the set of students at your school who are majoring either in mathematics or in computer science. We use the or part, which means it's either in mathematics or in computer science. Let's talk about the set intersection. There's what we call an intersection. So A intersect B is the set of all elements that are in both A and B, which is denoted by this symbol. So an element X belongs to the intersection of the sets A and B if and only if X belongs to A and X belongs to B. So here there's a condition that for it to be A intersecting B, the element that we have, it must be here. They are both in A and in B as well. So the shaded region represents intersection of A and B. This is similar to the logical and operator. So two sets are called disjoint. Two sets are called disjoint if their intersection is the empty set. If we have got A and B as disjoint sets, it means that we will no longer have this part, this shaded part. They will be actually totally separated, like this. We be having sets like this. Will be actually do not have this intersection because they are disjoint. In other words, we do not have elements in A which are also in what? In B. Like here, 1, 3, 5, 7, 9, and 2, 4, 6, 8, 10. A intersecting B is an empty set. Why? Because A and B are disjoint. Then there's what you call a set complement. A set complement. Take note of this. So a complement or not A is the set of all elements in the universal set, but not in A, which is denoted by A bar. This one by A bar. So all the elements which are not in A will form what? A complement. So these elements will be in our universal set, but only that they will be not in what? In A. So you shade the outside of A, but inside this rectangle, inside your universal set. So an element belongs to A bar, which is the complement of A, if and only if X is not an element of A. That is, X is an element of the universal set, but such that X is not an element in A. So the shaded area outside the circle representing A is the area representing A complement. For example, here for this set of vowels A, E, O, U, where the universal set is the set of letters of the English alphabet. Then A complement will be all the set of letters which are not the vowels, which are not vowels, like here B, C, D, up to Z, excluding these letters. Those will form what? A complement. So the complement operator is similar to the logical NOT and is reflexive. That is the inverse or the complement of that complement will actually revert to what? To A. Will give you what? The set itself. If you take the complement of that complement from that set. Then there's what we call a set difference. This notation, when you have got those elements which in a certain set but not in another set, we call it a what? A set difference. So the set difference which is denoted by A minus B is the set of elements that are in A with those that are in B subtracted out. Here we remove the elements in B. So another way of putting it, it is the set of elements that are in A but not in B. So A minus B is just as this. Can use A intersecting B complement. A intersecting B complement. Zvakafanana zvinhu twizvi. If I ask you to find the intersection of A and B complement, you see that that section, it will be the elements in A only. The elements in A only. Why? If you come here, if I ask you to shade the B complement, you shade the part which is outside here. And if I ask you to shade the set A, you only shade this part. So what is the intersection, which means it's just this part here, which is inside A, this part. So whenever I want to find the set difference of A minus B, you only have the elements which are in A but not in B. That's the set difference. So an element X belongs to the difference of A and B if and only if X is an element of A and X is not an element of B. I don't know if there is any question here. Don't know if there is any question. Okay, so there's what we call is where asymmetric difference. From the set difference, we've got what we call asymmetric difference. So asymmetric difference given two sets. The asymmetric difference is the set of elements that belong to either one or the other set, but not both. Here we are just excluding the intersection part for the symmetric difference, which means we are just considering the sets are the elements in A and in B, but not in both. But not both. So use this symbol for symmetric difference. So asymmetric difference B will be that X such that X is an element of A and X is an element of B. This one is an exclusive OR. That's the symbol that you use for the symmetric difference. It's an OR, which means X can either be the element of A or the element of B, but not both. So it can be expressed also in the following way. You can use this set identities, where you can have a symmetric difference B as A union B minus A intersecting B, which will give you this result after the distributive law. After using the distributive law, you get that result. So here is just an example for you, where you have got the universal set is 1, 2, 3, 4, 5, 6. This is the universal set that we have. And then you've got A is 1, 2, 3, B is 3, 4, 5, 6. And then we are being asked to find A intersecting B. A intersecting B. What could be our A intersecting B? Elements in A as well as in B. It's only 3, right? These 3. It's only these 3. Which means A intersecting B is what is 3. Note that A intersecting B is also a what? A set. It's a set. So you write the elements inside the curly braces. And then we've got what we call a union B, which means here we want the elements in A or in B. So 1, 2, 3, then we've got 3, 4, 5, 6. But remember, this 3 is a repeating element, so you don't need to repeat it in your A union B. So it will be just like 1, 2, 3, 4, 5, 6, just like that. Then there is what you call B minus A, which is the set difference. The set difference. So here, what do we need? B minus A, those are the elements which are in B but not in A. Remember, we don't need those elements which are in A if we have got this one. So, which are elements in B but not in A. So these 3 we do not need it because it is also in what? In A. So we only take 4, 5, 6. It goes the same way on A minus B here. A set difference of A and B. We need the elements in A but not in B. Elements in A but not in B is only this 1 and 2. These are elements which are in A but not in B. Then if you are being asked to find the complement of B, you just need the elements which are not in B, but they are inside your universal set. So elements which are not in B, but they are in the universal set. So we have 3, 4, 5, 6. But in the universal set, we've got 1, 2, 3, 4, 5, 6. So this one, 2 are the elements which are outside of what? Of B, but within the universal set. And then you need the set difference, which are the elements in either A or B, but not in both. But not in both. Like this here. We need those in A and in B, but not in both, which means we do not need this intersection. So you have 1, 2, 4, 5, 6, excluding the 3, because 3 is what is common. So we do not need this intersection here. I don't know if there is any question. Don't know if there are any questions. If there are no questions, here are some practice examples that you can really go on to do. Yes, there are some practice questions that you are supposed to do here. You are given A and B, then you are being asked to find A union B, B intersecting B, A minus B, B minus A, and as well as the Cartesian product. You can do all this. I think you can do all this on your own, just following what we are doing in this lecture. And also there's this question which says let A be the set of students who live within 1 mile of school, and let B be the set of students who walk to classes. Describe the students in each of these sets. A intersecting B, A union B. You are given a set and you are being asked to describe it. If you remember, when we started this lecture, we are having the set, the ways of describing sets. So there is the descriptive or the verbal way of describing a set, of representing a set. So I think this is the thing that you are being asked to do here, to give a sort of description which will be describing those sets. So that's the end of my presentation. I don't know if there are some questions. If there are some questions. Thomas, is that a hint? Okay.
Yeah.
Is it, do you have, you can go
Huh?
on. You can go on.
Can we go back to the last exercise?
The last exercise.
Yeah.
Where you are being to draw the Venn diagram for each of these combinations
No,
of the
the
sets.
one before this. Yes, there is this the first question. There is this D here. How do we go about it? Because I can't see any signal, any symbol between B and A, and the C one as well.
Which one? This one.
Yeah, yes, the D.
Yes, wait. You ask on this question or
No, I mean the one,
Mr.
the
Chimani.
one on top.
eh?
It says let A be. Excuse me.
Oh, this one.
Yes, that one. The
Eh?
D part of it. The D part of it. There is no
Okay.
symbol between B and A. And we have the C one as well. It doesn't have any symbol. How do we go about it?
You are being asked to
Just
find.
mention that first. I'm sure it's a network issue. On my page it wasn't showing, but now it's now showing. There are symbols there. There's a minus sign on both of those questions, C and D.
Ah, okay. You mean
Oh,
there is a minus sign between?
yeah, there's a minus sign. It's B minus A, which is the set difference of B
Okay.
and A. And then this one is also the set difference of A and B. like A minus B, B minus A.
Thank you, sir. Thank
It's
you.
okay. It's okay. You're welcome. Any others? Any question? Any contribution?